we're going to talk about active sound design today. If you're not familiar with what that is, we're going to touch on that, and so you'll have some sort of frame of reference, and then we'll talk a little bit about Siemens solution for active sound design. That's called Simcenter Testlab Sound Designer. I personally, as an ex-automotive noise and vibration engineer, had this question when I first heard about this product. I spent countless hours of my life trying to take sound out of the vehicle and make it quieter, right? So why on earth would we want to add sound to a vehicle? Well, primarily, or maybe most importantly from a legal perspective, a lot of vehicles, at least electric vehicles or vehicles with a fully electric mode, are now legally required to have a minimum noise. So when I was working at an auto company, we were always worried about exterior noise and being too loud. There's also now a minimum noise standard for electric vehicles to make, and that is for pedestrian safety. So you can hear them coming. Electric vehicles are a lot quieter internally and externally, and so that can provide an opportunity for danger for visually impaired who don't see the vehicle but rely on their hearing to perceive the vehicle and that sort of thing. So just general pedestrian safety. But you might also do this because you can. It's an opportunity. As we electrify the vehicles, we're going to start taking away some of the components that provide the primary emotional experience you have maybe with that vehicle, and that is the internal combustion engine, the roar of the engine, the way it sounds when you really accelerate hard, that kind of thing. That can be, in a large part, your brand reputation, right? The way the vehicle sounds when you operate it, that is your brand reputation. And so we want to protect that if we have an opportunity to do so, but also maybe provide some new brand value that we haven't before in using sound in a new and different way than we ever have. And then sort of maybe more importantly to some people, this can be an opportunity to reduce costs. We're taking a bunch of masking noise out of the vehicle by removing the combustion engine. The interior noise levels come down. All of a sudden, we start hearing those seat blower motors. We start hearing little cooling pumps, other little ancillary devices that maybe have been masked by that internal combustion engine all these years, and now they're starting to crop up. And so by providing some additional noise actively, we can craft that noise to whatever we want, but then also maybe mask some of those things we don't want to hear. So when we start to talk about active sound design, there are really two halves to it. There's the exterior noise, and that's going to be our legal stuff, right? These are mandatory things we have to do because of the legislation. We have to provide these acoustic warning signals, and that's being a responsible member of society. Additionally, we have an opportunity on the interior to replace some of that emotional experience for the driver of not hearing that internal combustion engine anymore, or replacing the sounds with something else. And so maybe we provide some auditory feedback and maybe some driving emotion that might be lacking in an electric vehicle. So this is optional, but is a big opportunity if we want to take on that opportunity. Keeping in mind that there is going to be some cooperation between the exterior legislated sound that we hear outside the vehicle and anything we do on the interior. If we're broadcasting AVAS sounds at 0 kilometers per hour and low parking lot speeds, we're broadcasting our brand sound to everyone, whether they are the owner of the vehicle or not. Right now, or in the internal combustion world, you had to get into the vehicle and drive it around to really participate in hearing that auditory experience. That's no longer the case. We're going to be broadcasting these things out all the time to everyone walking by. And so that's an opportunity to create and protect a brand sound. But then on the interior, we need to have that consistent messaging between the exterior and the interior for that brand sounding and how we want to identify our brand. And then we need to consider whether we want or how we're going to deal with any interaction between these two, right? Sometimes these exterior sounds are going to be loud enough that they will be perceivable in the interior. Maybe we want to take steps to prevent that, or maybe we want to use that to our advantage and sort of meld that into our interior sound design. There are three big sections here in this vehicle development process that we're going to talk about today. So I'm going to kind of direct your attention to some vertical columns first, and that is this upfront early design period over here on the far left. where we're creating sounds, we're deciding what we want this a brand sound to be, and then we're going to take steps to move that all the way along to deployment and industrialization over here on the right hand side. So we're going to create it over here, and in the middle we have a lot of work to do, right, to validate and tune that sound design, not only for the brand sound motivation that we had in the beginning, but also executing that and maintaining that initial concept into the specific vehicle and the speaker layouts and things like that that we're actually using. And then on the top half is the interior sound that we might have for our active sound design. And then on the bottom, we have a very similar process for the AVAS, or acoustic vehicle alerting system. This is the exterior minimum noise speaker that we'll have on the outside of the vehicle. So this is the overall sort of snapshot of the process. We're going to be walking through this for the rest of the hour here and just talking about kind of how Simcenter Testlab Sound Designer plays in all of these different environments. So 3 major guideposts. We're going to talk about designing active sounds with a complete tool set, and I'll explain more on what that means in just a second. Next, we'll talk about validating and tuning those sounds directly in the vehicle, and this is going to be a critical step because whatever we do up front and in the studio and at our desk needs to be validated and tuned in the vehicle, as you might expect. And then lastly, we'll talk about the AVAS compliance checks and AVAS design that are part of the Simcenter Testlab Sound Designer tool and how we can use those to our advantage. So first, designing active sounds with a complete tool set. So this snapshot here is of the Simcenter Testlab Sound Designer software. I'll show you that in just a minute or two, and I'll explain what all these different areas are, but this is where we're going to do a lot of our sound design in this process. So we're up front here, we're talking about brand sound exploration, talking to the artistic folks, the marketing folks for our vehicle. What is the image we want this vehicle to be portraying and how might that sound? And we're going to start creating some sounds. So how does this process work? Well, it really begins with an exploration with the art department and the marketing department and engineering and leadership, figuring out what that brand character is, and then translating that into some sounds, and then bringing in some other aspects of once we decide a direction, we want it to sound like powerful nature or whatever, marketing comes back with. We have some other tools we can use, classical things like engine orders. We might want to bring some of those in and blend some of our heritage into the brand sound, as well as making it something truly new and unique and creative so that we can spice up the sound and not just have it be a flat internal combustion engine remake, so to speak. And all along the way, we need this sound design or the sound genesis to be real sounding and alive. We don't want to just hear a pre-recorded loop just going back over and over. It's going to get really boring and stale. And so we really want this to be a living part of our driving experience. So we're going to do some upfront artistic stuff. We're then going to do some work to map that sound in terms of the direction we got from our art department, mapping that to some vehicle parameters like speed and torque and throttle position and things like that, so that we can decide how we want this sound to evolve and change as we drive the vehicle differently. And we want to do that in a tool that's going to be with us from the earliest days of dreaming up what we want this thing to sound like, all the way to vehicles start coming off the assembly line, and we want that tool that we've used from the beginning to be there with us in the final stage. And so we have consistency and familiarity with the tool and are very proficient with it, because this is going to be an iterative process. As we start mapping vehicle parameters to the sound, as we start driving that, getting feedback from leadership and customers maybe, we're going to then want to craft that and tune it maybe with some sound quality metrics and some other things in mind, so that it's truly becoming an enjoyable part of our vehicle driving experience, and not just some neat novelty that's playing through the speakers. So this is a bit of an eye chart, and I'll explain what we're looking at. Essentially, down here If you look at this section, this is the hardware. So there's some hardware associated with Simcenter Testlab Sound Designer, and this primarily this orange box. It's called the vehicle unit. And then this signature editor up here, think of this as the software. Okay, so we have software and hardware, and then we're going to essentially have different types of input. And so this section over here is where is the input going to come from? And the motivation for this slide is to show you that it can come from a bunch of different places, and that's making sure that the tool is usable at any stage, pre-hardware, with hardware, in production, that kind of thing. And then we have some output, right? Then we're going to be sending this audio output either to the vehicle interior speakers or the AVAS speaker on the outside, etc. So this hardware, if we now sort of highlight the design the signatures in the office sort of working flow, we have some manual editing of vehicle parameters. So that could be throttle, it could be speed, it could be load on the motor. All of those things we can be manipulating in a variety of ways, and we'll talk about those. Those get turned into CAN data, right? That the vehicle will be, that's the language the vehicle modules will be using to talk to each other. That CAN input goes to the synthesis hardware, and there's a back and forth between the signature editor or the software and what we're hearing. So we have live editing capability in the software as we're using the CAN messages and we're driving the vehicle virtually just here at our desk. We can modify how those sounds are shaped by those CAN parameters, and we can play an active role in that. And then we're listening in this stage. We're way up front. We're just talking about a theoretical vehicle program 5 years down the road or something maybe. And we want to start working on the sound of it. We can do that with Simcenter Testlab Sound Designer right here at our desk. And so we're just listening through headphones and playing with some sliders in the software. Later, we'll use this same hardware, and now we might have an actual vehicle that's producing the CAN. So now the CAN is coming from a real driven vehicle, and that's going into the hardware, and then that audio is being sent out to the audio system of the vehicle, right? We're going to be reusing the speakers that we use for the infotainment are going to be responsible for producing the active sound as well. The same tool, the same hardware is used from beginning to end. And you notice we're not directly necessarily interfacing with the hardware. We can load the libraries and the sound design onto the hardware, and it can be doing all of that synthesis live for us as we drive the vehicle around. So basic concepts, I'll jump over to the software here. So this is the Sound Designer software, and I'll give you a quick introduction to the interface and some basic operation of the software. So the first step over here on the left, this is sort of the project interface where I can load different vehicle architectures, different sound designs that I've made previously. In this case, the first step is to load my vehicle architecture, and you can think of this as a CAN layout. What messages for the vehicle are at what addresses and that sort of thing. The next is to select a sort of sound design architecture. In this case, I'll select this EV2 and that means it's a 2-layer sound design architecture designed for any electric vehicle, and we're going to use some granular synthesis in this case. Below that, I see 7 slots of existing sound designs that I've made previously, and they're all based on the same sound sample. So when I load one, you'll see a sort of a waveform up here in this window, and that is the starting sound. That is the wave file that I got from marketing or I made myself and said this is sort of the starting sound I want to build my sound design off of. And then using different approaches, I can create all of these different sound designs using that same starting sound, just different approaches by modifying how I adapt the sound to vehicle parameters and that sort of thing as I drive. So if I click this first one, we start to hear the sound design of the vehicle with the vehicle at this sort of base state. So I'll bring up this little interface, and here I can manually manipulate the CAN bus for the vehicle. So you see I've got kph, so I can manually adjust the vehicle speed, the load on the engine or the motor in this case, throttle position, and then RPM. And
for an electric vehicle, there's no typical mapping to RPM. It's really more for order synthesis, which we might do for an internal combustion engine to adapt or improve that sound. So this is that waveform. This is the starting sample. I'll play this for you. Okay, so that's the sound wave file I get from our designer or whoever, and that's going to be the basis for this sound design. Now, these windows below here where you see these diagonal lines, these are all different aspects of the granular synthesis that I'm going to modify. In this case, you see the vehicle parameter that I'm going to use to modify them, and these are all set to speed, SPD, that's vehicle speed. And then you see this guy over here is TRQ, that's modified by torque, or this Newton meter slider here. So as I increase the vehicle speed, slowly you see all of the cursors start to move. You see this blue window up here moving, and that is a graphical representation of the grain that I'm using for this synthesis. So I'm sampling that blue window, and then that grain is being modified per the relationships set out in these windows down here. So for instance, this guy, grain position, you see it's moving from at low speed here, so this is speed along the x-axis. It's at a position of 0, and as I go up to maximum speed, or 130 kph, it will move all the way up to 586 milliseconds. So I'm going to mute this for a second just so that you can sort of see the effect without having to hear it. So as I move my vehicle speed up, you see the position of that grain go all the way up to this moment here, or this value here, which is 586. I can modify this and say, well, at the maximum speed, I want you to be all the way over here at 900 milliseconds or so. And now as I modify my vehicle speed, you'll see that position is changing a little bit more drastically. Now, if I unmute this, we'll hear the effect of that change. So not a drastic difference in terms of position, but what will affect it is something like this grain duration, or even this pitch rate. So the pitch rate is telling me at a 0 kph, I'm at 0.5, or dropping it down half of an octave. And when I go to max speed, I'm going up a half octave. So it's a total of 1 octave change from minimum speed to maximum speed. So we'll hear that. Okay. And this does not need to be a linear relationship. I could have this go something like this. So it's going to sound much different now when I go up in speed. Okay, so this is graphically the relationship between speed and pitch rate, or the change I'm going to do in the frequency content, pitching it up or down. Similarly, of grain duration, the randomization of the pitch, the quantization for the pitch, all these different aspects of the way this grain here sounds, all mapped to, in this case, a vehicle parameter of speed. Now, if I look at this second sound design, again, same starting sound. This one's called jet takeoff, and you'll notice the grain duration is much smaller. As we go up in speed, it starts out at 342 milliseconds long and goes down to 10. And listen to the effect of shortening that grain as I speed the vehicle up. Okay, so quite different in character and emotion and everything, and it's all starting with the same base sound. Okay, and it's just because I've chosen to select a different grain length, a different position, and modified how that parameter changes with respect to vehicle parameters. So that will give you a quick overview of kind of what we're doing in the Sound Designer interface, and we'll look at some of the other features in just a minute.
So we'll talk a little bit about what we were looking at in that software introduction. We were looking at what we call the base layer. And so realistically, we think a successful active sound design is going to be made up of multiple layers. The first of which is typically linked to vehicle speed. As we saw in the software, all of those parameters were linked to speed, or most of them were. And this is sort of the base emotion of the sound. It's the base layer. It's going to set the tone for a lot of the recipe we're pulling together for this vehicle. And we have a couple different options of how we want to synthesize that sound. There are classic things like order synthesis. So this is generating sine waves with different phases and amplitudes to create some modulation to essentially recreate the sound for an internal combustion engine. This has been done for a long time. There have been devices that can do this, both for serious and not so serious uses. Order synthesis is a well-established method. Additionally, we have something called granular synthesis, and this is a slightly different approach. And this is not necessarily linked or even related to internal combustion engines or sounds that we historically have related to vehicles necessarily, but it gives us a lot of flexibility to be creative and come up with a truly unique sound that might capture the spirit of our vehicle. We also have some other newer features. Pitched playback, FM synthesis are some other generation modes we can use. And given a little more time, I can show you some of those sound design or generating methods and how they work. For now, we're going to kind of focus on granular synthesis just because it is so flexible and kind of shows nicely and gives you a feel for how much power you have in this software. So that's the base layer. On top of that, or in this case below that, we have what we call the torque layer. And this is for being able to change the sound for when we are in a high load condition. So if I just had a base layer and I just had that sort of speed sweep that I did for you, 70 kph would sound the same whether I get there in 5 seconds or if I get there in 50 seconds, right? If it's just based on speed, the character of those two acceleration profiles would be essentially the same. One would just happen faster than the other. Well, that's not how an internal combustion engine works, right? If you are getting on the freeway or you want to pass somebody and you really step on the accelerator pedal, it downshifts, the RPMs go up, and you hear usually a louder auditory feedback letting you know that engine's really spooling up and we're demanding a lot out of it, and we can feel that by being pushed back in the seat. That's different than if we're just gradually accelerating down an open road, and we want those two sound characters to be different, and a torque layer allows us to separate those. And then always there is something called this shepherd layer. And if you're familiar with the shepherd's tone auditory illusion, it's essentially a way of replacing frequency content in sort of a barbershop pole kind of graphical way. The barbershop pole, as it spins, it looks like it's constantly moving up. It's just an illusion that gives you this impression. We can do the same thing with frequencies, and so you can play this on a piano. Essentially, you play these constantly rising tones, and as your right hand gets up at the higher frequencies or the higher notes, your left hand starts playing those same notes, just lower on the keyboard, and your brain just perceives this constantly increasing frequency, and it can build in entertainment. If you're familiar with Nintendo 64, in Mario 64, there's a staircase that's infinite, and as you climb up that staircase with Mario, you're hearing a shepherd's tone. You'll just hear this thing that sounds like it's constantly going up over and over, and that's the shepherd's tone illusion. Also, Christopher Nolan uses this a lot in his movies to build tension, primarily in the war film Dunkirk. He uses this a lot in that movie. And if you've ever seen it, it's a very stressful movie. It is good, but I can't say it's enjoyable, but there's this effect being used there. All that to say, if we only had the speed base layer, as we speed the vehicle up to freeway driving speeds, those tones will now have risen up to a level where they're all going to be in the upper register, and it's going to sound kind of thin, maybe irritating. And so what the shepherd's layer does is it replaces those correlating frequencies on the low end, so we always have a nice, rich, full sound, and it never just becomes irritating. So order synthesis, this is, again, generating sound waves or sine waves and mimicking an internal combustion engine. But to do this in a smart way, we need to be able to, have different load tables. So again, matting the accelerator pedal, I want to hear different orders than I would if I'm just doing a slow speed sweep. And so the load on the engine should change the order content. We have that capability. But we also need to play some games with the variability of the frequency and maybe the phase to provide some realism to it. If we just hooked up a computer and said generate these sine waves and it was always the same, it's not going to give us a realistic feeling. And so the order synthesis engine in Sound Designer has some of these capabilities and can provide a more lifelike experience. So I'm going to play a couple sound samples real quick, just a standard internal combustion engine car. We're just going to accelerate and you'll hear just the base vehicle. So this is a combustion engine already, but we want to kind of soup it up, if you will. So this is no active sound design. Okay, so not bad. Here's some what we call sporty moderate active sound design.
And finally, full race active sound design.
So the other major sound synthesis tool we have in Sound Designer is called granular synthesis. And here we're really borrowing a technique that comes from the music industry, the entertainment industry, where we start with a sound sample and then we're taking small samples of that sound, which we'll call a grain. And that grain can vary in duration, so how much we're sampling, where we're sampling in the original sound, and then the number of grains that we're overlapping to produce a consistent sound, and how we're crossfading between those and that sort of thing. So we start with the base recording, and that captures some of the character that we want, but then we play games with the grains that we're sampling and how we're reassembling them, and we get a completely new sound out of that base sound. And that's really what we're doing in Sound Designer when we're doing granular synthesis. And then we're adding those randomization and making sure you never hear the same sound twice. It's truly being synthesized, created for you in real time.
Now, we mentioned there are multiple layers. I will show you how this manifests itself in the software, and we'll get an idea of what this is about. So this part of the interface that we've been looking at so far is really the base layer. It's usually controlled primarily by speed and sort of sets the tone for the overall sound design. Now we also have another layer operating in parallel that is based on torque, and so it's on this torque tab up here. Now you see there's a completely different sound sample up here, or at least it could be. In this case, it's the same sound sample that we're using for the torque layer, but it could be something completely different. It could be a lion roaring or something that I want to add some really different character for my torque layer. That would be possible. In this case, we're modifying the same sound in a different manner, and in this case based on torque instead of speed. So as I bring up the load on the engine, we see that grain moving, we see some filters actuating down here, and we see some gain. So the level is going up as a function of torque pretty drastically. And so this is a whole nother set of knobs I get to turn to sort of spice up my sound for when I'm in those high load conditions. When I'm really accelerating hard, I want the sound character to change drastically, and this is where I set that up. So it's speed plus torque, two layers operating together.
So where are we getting these vehicle input parameters, the speed and the torque? You're seeing me just sort of manipulate the software with some basic sliders. So this is a great way to start. You can do some real preliminary work. It's super fast and really easy. It doesn't make it super easy to compare A to B sound design approaches if you're having to manipulate the sliders, necessarily. And you can, of course, create potentially artificial scenarios, right, where you have super high load, but almost no vehicle speed, or 100% throttle, but 0% load, some things that can't really happen in real life. And so that's one of the drawbacks. But again, you're getting immediate feedback and doing some rough design work just with the sliders themselves. Later on, or maybe as you get the rough cuts done on your sound design, we can use some different tools. This section here is another module of software called Drive Sim. And essentially these are, you see them labeled RPM, torque, speed, and throttle. And these are the profiles we would get from a CAN. And so we can use this to manipulate all 4 of these sliders. These correlate right to these sliders over here. We can manipulate all 4 of them simultaneously in a highly repeatable way. So we can loop through this over and over and hear the sound and change our sound design so that we're getting a real iterative feeling. And those are identical vehicle parameters being applied over and over. And so we can get a real sense for how the sound design's coming together. And then most realistic, you can go out and record actual CAN messages from a real vehicle going around a test track or under a drive profile. And you can use actual recorded CAN to do the same thing we're doing in the Drive Sim. So that's the most realistic, reality-based way. And the software allows you to use these all interchangeably. And that functionality allows you to use this tool, again, way up front. There is no hardware. We don't know what's going to be. And as we go through and start getting hardware, and then now we've got a vehicle we can actually drive, let's go record the CAN and play with that to finalize our design.
Okay, this is a little video I'll play for you where we implemented several different sound designs and we compare those to the base vehicle. In this case, it's a Tesla Model S. So when I play the original, it's pretty quiet and you don't hear much sound at all as the vehicle's being driven. And you can see we have a video being recorded up here, and I'm replaying all of this inside Testlab Neo. And then we essentially say, well, what if we put an internal combustion engine into the Tesla? We can synthesize that. And then lastly, we kind of played some games just for fun with the granular synthesis, and we do sort of a more space-agey sound here. So I'll play this for you and give you an idea kind of what's possible. So this is the bass sound. You can kind of get an idea of what's going on up here. Again, pretty quiet per their design, but that might not be as exciting as we may want. So here's a truck. So you can see this, the Testlab hardware in here. So we're synthesizing the sound live while the vehicle's being driven, and we get to play with those parameters and things in real time while we're driving around. And lastly, this is the sort of space-agey one here. So that's granular synthesis example. Again, maybe not the sound we want, but it gives you some idea, kind of the flexibility you have and how creative you can be in terms of generating sound. The sky really is the limit.
So that's kind of our first bullet. That complete tool set from cradle to grave is Sound Designer, and the hardware can go through that whole thing. And then we want to validate and tune those sounds directly in the vehicle. So just doing the upfront desk work is not very realistic. It might get us started, but ultimately as we start narrowing down how we want this to really sound, we might get that finalized at our desk. Now we got to go put that in the vehicle. And the first time we hear it in the vehicle sound system, we're going to be likely disappointed or shocked at how different that is, because now we're using different audio drivers, different speakers, different speaker layout, etc. And so tuning process can really start in earnest once we get the vehicle. That's what we're going to talk about here. So now we're in this middle section. We're using the Sound Designer hardware and possibly some sound quality analysis to really fine tune this and affect our active sound design. So we use this vehicle unit, the sort of the front and the back are shown here in this slide. And you see there's an Ethernet connection, and this communicates directly with the laptop running Simcenter Testlab Sound Designer for in-vehicle tuning and modifications, controlling loading different sound designs, etc. It's essentially, you're in a working development context, and you can interface it with that directly. There are 4 audio outputs, so left and right, front and back. So 4 primary areas for audio output. And then we're reading a CAN bus in from the vehicle right into this CAN input here. Okay, so this is how we start doing real in-vehicle tuning. And in this case, we're showing maybe this is a prototype or mule vehicle or something that isn't exactly where we're going to be. We don't have any speakers that work, or the audio hardware isn't there or something. You can just use portable speakers, put them up in the corner of the dashboard, and start doing some in-vehicle tuning, actually driving and getting that next level of reality kind of built in. This video will show you a little bit of that process. Click through here, but he's kind of showing you the sort of rental car setup. So we've got some small speakers that we can put up where the speakers are gonna be. And then we have another bigger profile speaker for some low frequency. This would be more of your bass woofer type speaker. Again, we're just doing some real rough upfront work, but we can drive the actual vehicle, interface with the sound design in real time in the software, and do some further modifications. We're bringing the CAN right in from the vehicle and able to drive this around and do some real world modifications. Later, as we get further along, so you see this says leave the in-vehicle unit for final validation, we can load, there are 4 or 6 memory slots in here where we can load different sound designs. Here's version 1, 2, 3, and 4. We can load these right onto the vehicle unit memory and then give this to some leadership for the weekend, or say, go drive this. You can click through the different slots using a little interface on your iPhone or your Android phone. You can have those connect to the in-vehicle unit and then switch those in real time and just play around, see which ones you like better. And so now there is no PC hooked up, you can hide this stuff discreetly under the seat, and you're getting a closer step toward this is what it's really gonna be like, and let people spend some time in the vehicle using the hardware and hearing the actual sound design. So that's sort of the in-vehicle tuning process. And lastly, let's talk a little bit about the AVAS portion of the software and some of the tools built in here. So AVAS again stands for Acoustic Vehicle Alerting System. So this is the minimum noise requirements that electric vehicles or vehicles with a fully electric mode have to meet in order to be legally sold in countries around the world. And so now we're on the lower half, and we want to not only craft an AVAS sound that meets our design expectations in terms of branding and that sort of thing. We also want to front load the compliance, right? We want to know that we're going to meet the regulations when we get to the end based on how we've designed the sound and where the AVAS speaker is in reality and that sort of thing. In particular to AVAS, there are 3 specific challenges: creating a sound that resonates those brand values, again, because everyone's going to be hearing them at the stoplight or in the parking lot. That's just going to be audible to everybody. And in the vehicle development context, we're going to have a speaker, or maybe more than one, but we're going to have to figure out where that speaker is actually going to be mounted on the vehicle. Typically, it's behind the bumper or in the engine compartment or something, and that mounting location is going to affect the sound that gets out to the people, the pedestrians we're supposed to be warning, but also that's going to change the specific frequency content, how well it gets out there and what exactly gets out there. We'd like some tuning or some development tools to figure out where we should be mounting that speaker. And then ensuring compliance. Obviously, we want to know upfront whether we need to change our design or change levels or something to meet the government regulations. So different countries around the world have adopted different standards. Essentially, we've boiled down to two primary ones. There is the European R138, which is followed by the European Union, Japan, and China. And then you have the US, which has FMVSS 141. And it's very, very similar to R138. It is a little bit different here and there, but primarily they're all after the same thing. You're making sure the frequency content is going to be effective and it's at a certain level so that people will be able to hear it. So you have all these standards that are under operational conditions, so at multiple speeds, 10, 20, 30 kph, sometimes in reverse, as well as 0 kph, so just standing still. They want to have different aspects of the sound changing per region. So there's certainly a minimum noise, so it needs to be so loud in certain octave bands to ensure perceptibility. Some of the regulations have a pitch shift requirement. So as the vehicle's speeding up, we want to hear that pitch shifting or changing in a way that gives us the impression that that vehicle is speeding up and getting closer or further away. And then a volume change as we go up in speed. We want it to get louder because we need to warn faster. And so there's a bunch of aspects to these regulations: frequency bands, levels, pitch shift, and volume change, all of that. And so there's a bunch of aspects to the regulations we need to keep in mind. All of those aspects of these standards are baked into the AVAS check portion of Testlab Sound Designer, and we can help you ensure that you're going to meet these regulations. So in this case, you have some AVAS speaker. This is going to be the speaker that's mounted somewhere on your vehicle. There is going to be input from the CAN bus where it says how fast we're going, whether we're at park or in reverse, and how the sound needs to change. We're still bringing in CAN bus. And then we can use this CAN gateway to interface and still do some real-time tuning and development work with the Sound Designer software to craft that AVAS sound up front and put some of these changes into a working evaluation. In terms of the second challenge for AVAS, where do we mount the speaker? What we're really talking about is, I have three possible mounting positions in the vehicle, and I want to know which one is going to be the best for my AVAS design. And so what we can do with Sound Designer is measure some transfer functions, and it's a transfer function between the microphones where they're going to be tested on the side of the vehicle and in front of the vehicle, and mapping that to a voltage coming out of the audio amplifier. We measure the voltage coming out of the amp. We measure the pressure at all of these evaluation microphones coming through the actual speaker. We do that in a broadband sense, and we have an FRF, Pascal per volt. And we see for this mounting location, this is the FRF to, say, the front mic. And we see, as a function of frequency, what frequencies our speaker location broadcasts well to that microphone position, and maybe some areas where it doesn't do as well because of reflections or surface impedance or whatever, how much stuff is between our microphone and our speaker. And so we get some idea. So we measure multiple sets of FRFs. We can then load our sound design into the software for multiple operational conditions. If you can read it, it's 0, 5, 10 kph, reverse, 30 kph. And so we have a recording of the sound design, and we know how loud that's going to be, and we can essentially evaluate that sound design for each region under each aspect of the regulation and get an idea. Yes, you're okay, you're passing, or not okay, you've failed some aspect of that regulation. And we actually get level and octave band readouts for how we're performing, and it shows us where we're violating the criteria for that aspect of the standard. Okay, so we can do this way up front. We need our sound design. We need some FRFs that roughly represent our mounting locations in the vehicle, and we can get an idea before we ever have anyone listen or go to a testing site. We can have some idea whether we're on the right track as far as regulations go. So when we go to actually do this test, again, we have a CAN bus input, AVAS speaker, and some tuning, and then we can remove that PC and again do these vehicle evaluations and testing without needing that PC, and we just have the CAN feed right directly into our AVAS speaker. And so creating the right AVAS sound we're typically going to be using something like granular synthesis or pitched playback, something that allows us to craft a sound exactly how we want and get the brand character we like. The right speaker locations we can optimize through simulation and test multiple prototype iterations, all without necessarily involving an actual test. We can do all of that through simulation with FRFs and recordings of the sound design. And that allows us to front load that compliance and really get an idea up front whether we need to make changes to our sound design in terms of the frequency content or the level, or if we're going to be able to get there. If packaging is forcing us to use this mounting location, we can say, okay, that's not our first choice, but we can make these changes to the sound design to ensure we're going to meet those minimum noise requirements. Front load AVAS compliance by validating against various multiple minimum noise requirements. So I'll show you what that looks like here in the software. And I'll go to a different module. In this case, it's called AVAS check. And it will take me to this interface, which we saw a little bit of in the slides here. So I pick a architecture. In this case, I'll grab one of these sound designs. You'll see the sound design load up here. I can listen to these and hear the individual sound designs at various speeds, make sure that's all tracking how I think it should. And then I also have this tab. So right now, the transfer functions are just flat. They're not a real transfer function, but it does an evaluation for me right off the bat based on those transfer functions. And I see I'm not passing a significant amount of the regions and different aspects. So I can come in here to transfer functions and I can load some transfer functions. And these are essentially measurements from the left-hand side from my mounting location in the vehicle. And you see these are all Pascal per volt versus the frequency domain. And then I have FRFs to the various mounting locations and different mic positions. And so now if I come back here, I can say evaluate. And you see now with some actual transfer functions, I'm doing a lot better and I'm meeting the requirements in almost all of my areas. You see this is the EU standard, Japan, China, and so these will always sort of be the same because they all kind of go off R138. Then there's US 4 band and USA 2 band. Of course, being the US, we have multiple options for you in FMVSS 141, the 2 band method and the 4 band method. But in this instance, it tells me, okay, for 30 kph, my level maximum, I'm not okay in my level shift. And it says I have to increase at this speed by 3 dB. I only increase by 2.29 dB. Okay, so it tells me what aspect of the standard I'm failing at exactly what speed and exactly by how much I need to change. So I need to increase my volume shift by at least 0.7146 dB for that speed. So, okay, so I'm getting a lot of upfront specific advice or direction from the software that tells me what to change and how to change it. Incidentally, this last column over here is INT, which you might think stands for international. That's what I thought at first. It actually means interior. And so you can actually specify a target for an interior microphone as well. And so if we want to make sure our AVAS sounds are not heard from inside the vehicle, we can specify a target, measure an FRF to an interior microphone at the driver's position, and then assess based on all of these requirements as well. We can set a target level here. We're saying required, I don't want it has to be 40 dB or less, and we're measuring 71, basically 72 dB. So we're way over that target. And so that allows us to set these targets however we want to ensure that our AVAS sound for our vehicle is not going to make it in or is only going to be at a certain level. So that's a little bit about the AVAS check module and how it can help us up front know whether or not we're headed in the right direction. As far as deployment, as we go into industrialization and we're trying to get out of the development world and into the mass production world, we now want to kind of take that sound design and all of our work along the way and bake it into the vehicle and have it be part of that vehicle. And so we have a couple options here. But ideally, you are using similar tools between development and mass production, and that is sort of ensured by the way Testlab Sound Designer has those sound libraries and the synthesis engine. Those can be ported directly on to an audio chip, the DSP, that's actually doing the infotainment audio processing. The libraries that were used in the vehicle unit, the exact sound samples, the libraries we use to change that sound are all ported over with our help to the tier 1 audio supplier. And that synthesis engine is actually handled by the tier 1 audio supplier on that audio processing chip. And so the experience you finalized and get down to in your final steps of development are recreated in one last step and can be finalized for mass production. Well, thanks everybody for attending, and hope to hear from you soon.